Keenan Burnett, who is a PhD student under the co-supervision of Professors Barfoot and Scholig at UTIUS. And Keenan is going to tell us about the following. The title, do we need to compensate for motion distortion and Doppler effects in radar-based navigation? So Keenan, whenever you're ready, the next 3 minutes are yours.
All right, thanks, Jonathan. I'll just repeat the question. Do we need to compensate for motion distortion and Doppler effects in radar-based navigation? Self-driving vehicles today are being designed and developed to operate in sunny conditions such as California. However, there remains a large gap between operating in these ideal conditions and getting these systems to work in the snowy climates that we're used to here in Canada. In order to address this challenge, radar is currently being revisited as an alternative to vision and laser-based systems. Due to its longer wavelength, radar is more robust to inclement weather conditions such as rain and snow. So radar is really the key to getting self-driving cars to work in Canada's climate. So far, existing works up to this point have made significant progress in applying radar to odometry and place recognition. However, these works have so far ignored the impact of motion distortion and Doppler effects on radar-based navigation. The radar sensor that we're talking about rotates in order to provide 360-degree coverage around the vehicle. Figure A shows what this looks like when the vehicle is stationary. So what happens is that when the vehicle is moving, the range measurements become distorted in a spiral fashion, as shown in Figure B. Radar sensors of this type calculate range by measuring the difference in frequency between the received and transmitted signal. However, when the vehicle is moving, the relative velocity between the sensor and its surrounding environment causes the received frequency to be altered according to the Doppler effect. Figure C illustrates what this effect looks like. The Doppler effect here is analogous to what happens to the pitch of a police siren as it's driving by. The frequency of the received signal in front of the vehicle will be higher. So it should be noted that as the frequency increases, the received range of targets will decrease. So our proposal is to use a motion compensated estimator to calculate the linear and angular velocity of the sensor directly. We can then remove the motion distortion and Doppler effects from the radar scans. In terms of experiments, we perform radar odometry on the Oxford radar dataset and metric localization using our own data-taking platform. In Figure A, we plotted the error resulting from our odometry solution. In red, we have the baseline algorithm, which ignores motion distortion. And in blue, we have our motion compensated estimator, which is much closer to the ground truth. In Figure B, we have a bar plot, which summarizes the results of our metric localization experiment. The results here show that our approach significantly reduces the localization error. So to summarize, our results indicate that motion distortion should be compensated. However, the Doppler effect can be safely ignored for the odometry problem. Accounting for both of these effects is computationally cheap, but requires an accurate estimate of the linear and angular velocity of the sensor. Thank you.